Today, we're diving into a force that's silently at work all around us, a force that can turn mighty structures into nothing more than dust. We're talking about corrosion, and trust me, it's a story that's so much bigger and way more fascinating than just a little bit of rust.
So, have you ever really thought about this? You see a brand new, shiny iron nail. You leave it out in the rain and, well, sooner or later, it just crumbles away. We've all seen it, but what is actually going on there?
While that nail is in a fight for its life, it's losing an invisible but totally relentless battle. And that battle has a name: corrosion. It's happening to metals all over the world, every single second of every day.
This definition is actually pretty cool. We tend to think of corrosion as just decay or failure, but it's really a natural process. We work hard to refine metals from their stable, natural state, like an ore, and corrosion is just chemistry's way of saying, hey, I want to go back to how I was. It's not a bug, it's a feature of the universe.
Okay, so let's start with the face of corrosion we all know and recognize. Good old rust. The technical name for it is uniform atmospheric corrosion. But really, it's the most common type out there, and it's the one we're all familiar with. And the chemistry behind it? Surprisingly simple. It really just boils down to 3 steps. First, you've got your iron. Second, you just add oxygen and water, and that can be just the moisture in the air. And third, boom, those ingredients get together and form hydrated iron oxide, which is just the fancy name for that reddish-brown flaky stuff we call rust.
And certain things can really put this process into overdrive. Higher temps, more humidity, even pollution in the air, it all speeds up the reaction. If the surface of the metal is rough, that gives the rust more places to get started. And of course, the longer you leave it out there, the worse it's going to get.
Okay, but now this is where things get really wild. What happens when you put 2 different metals together? Well, they can literally create a tiny little battery, which leads to a pretty shocking phenomenon called galvanic corrosion. So here's how it works. You take 2 different metals, you stick them together, and you put them in an environment with an electrolyte, which can be anything from salt water to just damp air. They actually create an electrical current. One metal, the more active one, becomes the anode, and it starts to corrode like crazy, while the other one, the cathode, gets protected.
And this right here is a perfect example of what we're talking about. It's a tale of 2 coatings. If you put a zinc coating on a steel tank, zinc is more active. The zinc basically sacrifices itself. It corrodes first, and the steel stays safe. That's a great pairing. But if you coat that same steel tank with copper, which is less active, oh boy, you've just made things so much worse. The steel is now forced to be the anode, and it corrodes super fast, all to protect the copper coating.
So, what's the bottom line here? It's actually a pretty simple rule to remember. If you want to protect a metal with a coating, you have to use a coating that's more active or less noble than the metal you're trying to save. This is the whole idea behind everything from galvanized nails to the big zinc blocks they stick on the hulls of ships.
Now, so far, we've been talking about the kind of corrosion you can see spreading across the surface. But some of the most dangerous forms are the ones you can't see. These are corrosion's sneaky attacks, the hidden killers, and they're so dangerous because they can cause a total failure with very little actual metal being lost.
We're going to look at 3 main threats. First up is pitting, which is exactly what it sounds like. It's like a tiny cavity in a tooth, boring deep into the metal. Then you've got stress corrosion cracking, where you need a combination of tension and a very specific chemical for these nasty cracks to grow. And finally, intergranular corrosion, which attacks the very structure of the metal from the inside out.
Let's talk about pitting for a sec, because this one is particularly nasty. It can get started from just a tiny impurity on the surface, or even a single drop of dew that concentrates some corrosive stuff. A tiny, almost invisible pit can dig its way deep into a pipe or a beam, and then catastrophic failure, seemingly out of nowhere.
And stress corrosion cracking? Man, that requires a perfect storm. You need a metal that's under stress and a very specific corrosive chemical. It's all about these deadly duos. You get stress steel near nitrates or copper alloys anywhere near ammonia, or even something as common as stainless steel in salt water, and you've got the recipe for disaster.
And then there's intergranular corrosion. The best way to think about this one is to imagine the metal's internal structure is like a brick wall. This corrosion doesn't attack the bricks, the metal grains, it attacks the mortar holding them all together. It's a disease of the metal's skeleton, weakening it from within. This is a massive problem in welding, especially with stainless steel, where it can cause something called weld decay. All right, for our last type of corrosion, we're looking at a real brutal 1-2 punch. This is what happens when you combine a chemical attack with good old-fashioned physical wear and tear. It's called erosion corrosion.
So picture a fluid rushing through a pipe. The fluid itself might be corrosive, but it's also physically scrubbing away at the metal surface. That mechanical action literally scrapes off any protective layers that might be trying to form, exposing fresh metal to the chemical attack, over and over and over again.
And yeah, as you'd probably guess, how tough the metal is makes a huge difference here. Softer metals like lead or copper are way more vulnerable to this kind of attack than much harder materials like chromium or high-carbon steel. And what really causes this to get out of hand? Turbulence. Simple as that. Anywhere a fluid has to change direction really fast, like at a sharp bend or a valve inside a pipe, the flow gets all chaotic. And that turbulence just massively ramps up the physical wear and tear, creating these hotspots for really severe erosion corrosion.
So after looking at all these different ways metal can just fall apart, it's pretty easy to see corrosion as this purely destructive, negative thing, right? But if we just step back for a minute, what is this constant, invisible battle really teaching us?
It reminds us that nothing, not even the strongest materials we can make, exists in a vacuum. They are in a constant, dynamic dance with their environment. The air, the water, the stress they're under, it all matters. And by understanding these many faces of corrosion, we can learn how to build a stronger, more resilient, and ultimately a safer world for all of us.
So I'll just leave you with this final thought. Is corrosion simply decay, or is it something more? A fundamental reminder from the universe that nothing is truly permanent, not even the strongest steel. It's definitely something to think about.